Yes, it's started. It's started, yeah. And the screen is visible, right?
Yes, ma'am.
Yes. Okay. Cool. So, yeah, what were we doing yesterday? We were looking at this notion of approximate Q learning, right? And so the idea was that, I mean, the difficulty with Q learning was when you have a huge number of states. So you do an update to your Q values. So the Q values are a function of the state and action. And whenever you see a transition like this, whenever you observe such a transition, you make this kind of an update where you have the current Q estimate plus alpha times some difference between the new sample that you see and the original value. Okay, so this is how Q learning was, and you need to have at least as many samples as your number of state action pairs. Okay, so that's, I mean, at least that much. So maybe even 10 times that number. Okay, so that's the issue with Q learning, and typically doesn't scale very well. And that was a motivation for going into approximate measures, where you try to generalize the Q values that you learn. Okay, yeah, sorry about that. Yeah, so on Q learning, we were doing the approximate, we were moving into the approximate notions. And then what we saw is that you try to generalize what you learn about a particular state to some other states. Okay, and there we had this notion of features. Okay, so for each state action pair, you define this notion of features. Okay, so a couple of n features. So these are all features, a set of n features. And what you do is, instead of directly going with the Q value, you take a linear combination of these features. Okay, so that's, and you try to learn these weights. So that's what we were looking at yesterday. So, were there any questions on this idea? I just want some response on this, like whether it was clear, or whether you got this idea. So you can type into the chat. Advait, okay, Ravindra says it's clear. It was clear. Okay. All right. So, cool. Wonderful. So, so as we went forward, I told you how you can, estimate these W's. So instead of estimating the Q's directly, now the focus is on getting the values of W's. You maintain some estimates, and as and when you see a sample, this is the update that is done. Okay, so you will see a transition like this, S A S dash R, and then what you will do is you will take the old value of Wi plus alpha times the difference. The difference is just exactly the same difference that was used in the vanilla Q learning. And there is an additional term here. Okay, so this part, it's weighed by each of the FIs, the exact feature value itself. And this update you need to do for every feature. Okay, so after the class, actually, I mean, Sanjay asked me one question. So I realized that I'd missed pointing out the intuition for why this value was needed, this FI was needed, or what does it signify? So think of it this way: the Q values are a combination of these features, right? And if a particular feature value is very small, if it's close to zero, then in some sense it doesn't really affect the Q value. Okay, so even it shouldn't affect the update as well. Okay, you see a sample, so that feature is not very important, so that's why you have it's weighed by this term. Whereas if the feature value was very large, then it's a very significant value, and so that's why it needs to play a greater role. This particular sample needs to play a greater role in the update of WI. Okay, so that was the intuition for having this. And what we discussed was also that you can have different kind of models. So this was a particular case called a linear Q function, but you can have polynomials. So one is you have as the weights, as a polynomial the weights, and other possibilities you can also just have something like this, polynomial in the features themselves. Okay, this is also a possibility you can have. Of course, this is still a linear function because it's a linear combination of these features, but it's just that you have powers of the features. So that's also a possibility. And yeah, you can build a whole range of Q functions, very complicated looking ones. If you have enough data, if you are able to get enough episodes, you can learn reasonably well. Okay, and nowadays there is this focus on using neural networks here. Okay, so it's more towards the deep reinforcement learning idea. Okay, so today what I will do is I will give you some idea about why this update works. Okay, what's the underlying principle being used? Okay, so the underlying principle is just a machine learning algorithm, which is called linear regression. So are you guys familiar with linear regression? I mean, I know probably it's not part of a course, or was it a part of some course?
No, ma'am.
Okay, but have you seen it anywhere? It's not done in a course, but are any of you familiar with it? Yes, Satvik is familiar. So you would have probably read about it, right? I mean, it's a very commonly used algorithm now, right? So a couple of you have seen it. So let me just, provide a quick primer for those of you who would not have seen it. So the idea in linear regression, so let's just do a little bit of basics of linear regression. So this is the problem where you have some real valued data that you want to predict. Okay, for instance, like there are all of students who are applying for some jobs, and you find, I mean, you want to know what is the income. Okay, what is the income for people? Okay, in this country. So maybe a even broader question. So what is the income for a person? Okay, so this is something maybe that you want to predict. Okay, and this is a function of many parameters, right? So you can think of the income as dependent on maybe the age, right? So if you're younger, maybe you have a good chance of getting a high income, and maybe somewhere in the middle age you get a lot of income, but afterwards maybe you retire and your income drops. Okay, so there's a dependence on the age. Okay, that could be a feature. Then maybe your educational qualifications, right? So if you are, and where you studied, right? Where you studied. So these are some things that can matter in deciding the income. Okay, and so what happens is these are the features. So there can be many such features. Okay, so we will denote this by a value x. It's a feature vector basically, and the income, that is something we'll denote as y. Okay, so typically what happens is you'll have some data on all these, like you'll have a collection of these x y pairs, okay, which I'll call as D. This is like a data set that you will have. And based on this, you want to, if you get a new point, if you get a new collection of features, so this is a new person that you are seeing, and then you want to think of, what could be this person's income. Or if you are somebody who's recruiting, then you want to see that, what is the right salary to give for this person, depending on all these factors. Okay, so here you want to do a prediction. What is the y value? Okay, so y test. For this instance, what is the prediction you want to make? Okay, so this is the problem in linear regression. And so you need some underlying model here. So what you typically do is, your y's are maybe some points like this. So this is just a case where there's a single feature. There's a single feature x, and this is the predictions or the actual values. Now, what you assume is, I mean, you don't know really anything about what is going to happen, except that you see these data points. But you need an underlying model for your data. I mean, an underlying model for, something about what you assume. So what you could potentially assume is your income. So this is in your understanding. So I'll put this as a hat. Why hat? Because this is a model, and you will model this as, maybe it's a linear combination of all these features. So W1 times F1, the first feature, plus W2 times the second feature, and so on. Okay. So W, maybe if there are some N features, or let's call it D features, small d. So D features, and maybe, this is a model you assume. And now what you want to see is, you want a nice model. So you don't know these W's, and you want to learn it from the data. Okay. And intuitively, what this means is you're assuming some kind of a line like this, right? And the true value is something that you see from the samples is y, but for a given value of x. Okay, so for this value of x, what you get from the data is this y, but as per your model, this is the value y hat. Okay, and you want to learn these w's so that you're able to make predictions as best as possible. So if you have a new test point, what are you going to do? You're going to, like, if you have some estimates w1 to wd, what you're going to do is you'll compute this number w1 times f1 of x test plus w2 times f2 of x test, and so on. And that will be your y hat test. So that's what you will compute. Okay, and that you will say is your estimate. Okay, so that is the idea in linear regression. So how do you learn these W's, right? Since you already have some data, so let's just say this is data points are like I is from 1 to some capital N. Okay, there are N such points. So you have Xi and Yi. Okay, so I hope the notations are not too confusing. There's a D and an N. Okay, so D is the features and N is the number of points, your samples. Okay, so what you want to do is you want your prediction to be as close as the true value. Okay, your prediction, you want it to be as close as what you see for these tests, for these training points. So these are the training points. Okay, and typically what you solve is an optimization problem where you want to minimize the error. Okay, so the error in your prediction is just you take each point, so I from 1 to n, and this difference, right, yi minus y hat I. Okay, so y hat I is what you would predict, and maybe the square of this, because you don't care on which side of the line you like. Even this is as good an error as, I mean, if you predict something here that's yeah, if the y was actually here, it's the error, you don't distinguish too much. Okay, so you try to minimize this kind of an error, and typically there's a half that is written here just for convenience. Okay, so you will see why that's done. Okay, so is up to this clear? I mean, you probably might have seen it, but I just want a response. Whether are there any questions here, or shall I proceed further?
Ma'am, that the function provided is only on one feature, or that is on every feature?
This function, so f1 is a number, f2 is another number. Okay, so that those are all. Okay, I get what you're saying. Like whether x's themselves are the features, right? So probably that's your question, right?
Yes, ma'am. Yes.
Yeah. Okay, so that's right. So actually, yeah, I mean, in this case, I just wrote it for like complete generality. Like you can define some functions on some instance, on the input instance, but you could also just write this as w1 x1 if you're working directly with this vector. So xi could be of something like which is in Rd, like a d-dimensional vector, which itself is the features, right? So in that case, you would write it as w1 x1 plus w2 x2 plus so on up to wd xd. Okay. Yeah, so this is one possibility. And more generally, you can also define some kind of features even further, right? With these, there's some representation of features that you have, but maybe you can go even further to take do something more with these features, with these x's. Okay, is it clear or not?
Ma'am, and how we
Yes,
gonna
ma'am.
represent this like d-dimensional vector into a graph?
into a graph. Okay, so this one here, I'm only taking the case of a one-dimensional feature.
Like just the age feature, for example.
Which one? Can you say that again?
Like just the age feature, for example. You just you just
Age,
plotted
yeah.
is x.
Exactly. So I'm just taking the age here and I'm writing it. I mean, just there's
So
just
ma'am,
one. There's just the next
if
one.
we are given age and education together, like
Mm-hmm.
we are given a 2D vector, then how we gonna plot that? It's in
So
a,
that
like a
is
3D.
gonna. It will be a 3D plot exactly. So you'll have
Okay.
two axes with the age, one axis on with age, and the other axis you'll have education, and the final axis would have the y values,
And ma'am,
right?
how we gonna write this weight function for that 2D vector?
Yeah, so if you're going to directly use the x's, so maybe let's just write it that way instead of writing it as f1. It might be a bit confusing. But generally, you can write any complicated functions also here of the features. Um, what happened? Okay, so just let me just write this as w1 x1 plus w2 x2 plus so on plus w dxd. Okay. Yeah, so in the case where you have age and education, if you're going to use only age and education, what you will say is y hat is w age times x age. Okay, so the age component of your features, of your feature vector, plus w, education times x education. Right, so if these are the only two features, you will write your y in this form. Okay,
Yes,
so was
got
that,
it, ma'am.
that was Sahil?
Yes, got it, ma'am.
Okay, okay. So, are there more questions here? Um, some responses. Is this clear so far? Or probably the F and the X that probably might have confused. Yes, it's clear. Okay, cool. Okay, great. So, so this is the function that you are now trying to optimize. Okay, so this is actually it's giving you a sense of an error in your predictions. So the minimization needs to be done with respect to W's. Okay? Now, where does a W feature here? Which part of this function is going to be dependent on W? Can you tell me?
Y hat.
Y hat, right? So the W's will come here, okay, because it comes in from this part. Okay, so let's just write it, just for completeness. So what this is going to be is actually for each instance you take, you're going to get yi minus, so y hat I is just, w, so there's, okay, so let me call it wj times x, I'll call it ij. Okay, so this is xij means it's for the ith point, for the ith sample, uh, the jth feature. Okay, so I hope this distinction is clear. Okay, because you have an iterator over the number of over the training points as well as over the features. So that's why there's an xij. Okay, and j is from 1 to d. So this is your error square of this, and this you want to minimize, and you want to find the w's. Okay, so you have the y and you have the x's because those are the features, and you want to get the w. Okay, so in general, this comes under a class of study called optimization. So perhaps you will, in the next semester, I might probably offer an elective course in optimization. So you'll see more details about how to solve these kind of problems. Of course, you know some things, right? Like to minimize this function, one way is you take the gradient with respect to w, and you can set it to 0. Okay, so if this function, if I call it as, let me call it j, capital J of w, okay, because for all practical purposes, it's a function of w and that's what matters to us. And one thing is you can take the derivative with respect to each component, try to set it to 0. Okay, do this for all the components and then try to get a solution for the w's. right? This is something that you would have seen in your calculus classes. Okay, so more generally, this kind of a technique might not give you a closed form solution. So the idea is that you solve this for the value of w, for the best value. Sometimes it works, it depends on the function, but it may not always work. Okay, so you need other methods for it. And one method is called a gradient descent step. So the idea is, just think of it as, there is, okay, so function looks something like this. So this is a function, maybe j of w. Okay, so this is the w axis. Okay, so I'm just writing it in terms of one dimension so that the idea comes out. So what you do is you start somewhere. Okay, maybe your current estimate is something here. So this is your current estimate. And so the corresponding value of j of this estimate, so let me call it w naught. Okay, so this is the 0th estimate. So you're starting here at a very bad value. You want to get here. Okay, so this is the value that you want to reach. So it's like a hill, right? I mean, you want to come down the hill some way. So, from here, like you can try to, jump through any ways. There are like different directions. So maybe you can, the directions are in terms of W. So you can maybe go this way or you can go this way. Okay, so these are the only two possible directions here because it's in one dimension. So if you go in this direction towards the right, maybe you can take a small step and just land up here. So if you take a small step, you come here. If you take a very large step, you can come maybe somewhere here. Okay, so there are a couple of things you want to try out. And generally what you do is there's a particular direction. Not every direction may be good for you to go in. Okay, in this case, this is the right direction to go. Okay, if you go towards the left, it's a bad direction for this example. Okay, and then generally, how do you generalize this idea to higher dimensions? Okay, so that's the rough flavor. Okay, so what you do is you have a current estimate, you have your W old, and what you do is you increment it by some direction. Okay, so the particular direction is as what is given by the gradient step. Okay, so the gradient, if this function j is there, and if you take the gradient with respect to w, what are you going to get? What is the size of the gradient? Just a quick calculus recap. How many components will, if you take this, I'll write it as del j, right? Del j with respect to w. So that is the gradient of j with respect to w. How many components does it have? Is it a single number? Is it a vector? Is it a matrix?
Vector. Vector only.
It's a vector, right? So the components are basically, you have dou j by dou w1 and so on up to dou j by dou wd. So if there are d components, this is going to be the vector, right? And so this w old is also a vector. And what gradient descent tells you is you go in the direction of the negative of the gradient. Okay, and maybe you have some kind of a step function. So this alpha is like how far do you go? So should you take only a small step in this direction, or should you go far in this direction? Okay, so that's the value of, that's what alpha is. And this is what is called a gradient descent update. Okay, so this is gradient descent, and you keep doing this. So now again you come to, suppose you decided to come till here. Now again you take the gradient of this function. So this is where you are now, the function value is this. Now you take the gradient here, and then you go in the direction. So here the gradient is again, it's the negative gradient, so it's going to be in this direction. Okay, so the gradient always is going to point in the direction of increase of the function. So actually the gradient will be in this direction, but since you're taking the negative gradient, it will be in the opposite direction. Okay, so MBA, you'll see more of this hopefully in the next semester if you're taking the optimization course, but this is just to give you a flavor. Okay. And now if you substitute this here, right? So this is now the function that you want to optimize. So can you tell me what is dou j by dou w1 here? What is it going to be? So this is the function jw. So this whole thing, half times this. So what is the value of dou j by dou w1?
Sigma of that value in the brackets.
Mm-hmm. So
And
that, yeah, so there's a 2 times this and it gets cancelled with the 2,
cancel.
right? So you get this term itself, yi minus the same term, wj x ij,
Multiplied by x1
multiplied by
XI.
x
x1.
xi1, right?
Yeah.
Ith sample in the first, okay, the first feature. Okay, so generally this is the update, and for any j you can write this. Okay, so for the jth feature the same thing will happen. You have over all the points you take, right? So I shouldn't confuse this j and this. Let's call this j dash. So j is 1 to d wj xj times you have an xi j dash. Okay, so generally you do this, and that's how you update your w's. Okay, and so in short, you will get w is w um, minus alpha times this quantity. So this is just nothing but it's just whatever yi you had minus y hat, your current estimate, right? Times, I think there's a negative xi also, right? Because the gradient will have a negative value here,
Yes,
x,
ma'am.
right? So into minus xi hat. So this minus and this minus, becomes a plus sign. So you have this plus alpha times yi minus y hat I, okay, times xi. Okay, so this is now a vector. So I'm writing it in a vector form. Okay. So yeah, are there any questions with this update? Has this been clear? Is it too fast or is this right? Response. Yes, yes, okay. All right. Okay. So I guess this has been clear. So just stop me, okay, in case something is unclear. There's nothing to be shy about not knowing this. Okay. I mean, it's probably the first time you're seeing it in a course, and if you have not seen it other places also, it's absolutely fine. Okay. So yeah, so this is the update you will make for W. And so what you see here is this was a feature, right? This was a feature, and this is some kind of a difference term, okay? And there is some alpha, which is it's kind of a tuning parameter that you have. Now, relating this back to our Q learning example, like how did we have our Q learning update? Right? So this was the Q learning step. And if you see, it's exactly the same thing. Okay, so let me just copy this down so that you can compare the two. Okay, so this was the Q learning step in blue that you see, that was a Q learning step. And here the key thing was that there was a single sample. Okay, so remember what we saw was just one transition. So you had SA S dash R. That was the only sample we saw, and so here this I that we have for the linear regression case, it's just there's no summation now anymore for the Q learning part. So this difference corresponds to this quantity. So it was so here, if you remember, this was like R plus what was it? Can you remind me what this was? You had an
Gamma
new,
times max over A dash.
yeah, max over A dash. You had
Q of
a
S dash A dash.
Q of S dash A dash. minus Q of SA, right? So it's as though this is the sample that you got, right? So this was playing the role of yi here. Okay, so it's just a single y. Okay, so this was playing the role of y, and this q is playing the role of y hat. Okay, so it's exactly the same thing, and this feature here, fi, is playing the role of this xi. Okay, so this is also a feature here. Okay, so so this is exactly gradient descent step in linear regression, and that's how it's plugged into Q Learning. Okay, and that's why it actually works. Okay, so what I want to do now is I just want to show you some demo of how you've seen the theory. I want to just show you like why it works in practice, or how it works in practice. Okay, so I will use your whatever you're going to do in your labs itself. Okay, so I hope this has been clear, and if there are any questions, please interrupt. Okay, yeah. Okay, so what I will show you first is I will show you how Q Learning works with Pacman. Okay, so we're going back to the Pacman example. So okay, so what were the transition probabilities, and how does it translate in Pacman? Okay, so unlike grid world, where if you take an action, the thing was that you could go right but still not end up right. So that was the setting in grid world. Okay, but in Pacman, what we think of as the actions and where's the randomness coming in. So that's because of the ghosts which are also there. Everything is modeled in one state, and now you take a right action. Of course, you will go right in Pacman. There's no issues there. But the issue is you don't know where the ghosts are going to be. So in that sense, there is an uncertainty about the state, about the next state. Okay. Of course, you can also bring into Pacman these aspects that, if you go right, you don't know if you will really go right. I mean, is there some controls in the keyboard that will get messed up? Those kind of things also you can model. But here it's just about, the positions of the ghosts that you don't know. Okay. So I will just show you one. I'll start with this small grid example. So we will see how Q Learning performs. So remember that you start off not knowing anything about the system. You only know what are what are the actions that you can take. You know your current state. You know what actions you can take, but then you don't know where you're going to land up. You don't know where the goals are. There's absolutely no idea. You don't have any idea of the rewards here. Okay, nothing is fed to it. Okay, so let's just see one demo. So I'm just running it for 10 episodes. Okay, so it's a small layout. Okay, so it's dying the first time. It's again dying. Okay, because it doesn't know what to do. Nothing has been told to it. And slowly it's trying to move around and maybe get a better idea. Okay, so it's trying to do some exploring. It's moving here or there. But every time it's dying, but it's still learning something. Okay, so it's trying to go, and if you see here, the record is that every time it has lost, it's gotten eaten up. Okay, and every time it died. Now let's run it a little longer. So I won't show you all the, I'm going to run it about 2000 times. So you won't see this visual 2000 times, okay, fortunately. But you will just see some information getting displayed on how the scores improve each time. And in the last, you'll see after these 2000 episodes, you will see like 10 rounds of, how the Pacman is doing now, after 2000 episodes of training. So let's get started. Okay, so what you're seeing here is, the average rewards in the last 100 episodes. If you see that quantity, that is getting, it's improving each time. Okay, so that's getting displayed here. And you see, like you started off with negative quantities, and now it's become like 257. It's improving by and large. Okay, sometimes it reduces. And this is now it's actually playing. And you see it's doing much better, right? It's actually winning now. Okay, it started off at a very bad state, not knowing anything. You saw the 10 episodes of training, and given enough training episodes, it could identify what is a good strategy, right? every time it's figuring out a path. It's also going very close to the ghost. Okay, this is something that we wouldn't dream of, at least I wouldn't dream of doing. And see that it has 1 at every instance. Okay, so this is how Q learning actually worked. Okay, so this was vanilla Q learning. We didn't use any notions of approximate Q learning here. Okay, now I just want to show you a slightly different layout. This is the medium grid setting, where again we are just going to do the vanilla Q learning. So I'll just show you the layouts, like how it is different. Okay. Yeah, do you see both the layouts on the page, on the screen?
Yes, ma'am.
Yes. Okay, so the one on the left is the one that you just saw now. Okay, so it's that layout. And here with about 2000 episodes of vanilla Q learning, it was able to do reasonably fine. Okay, now the new layout is actually in terms of the size, I mean, the entire size of the layout, probably it's not very different. It's just a little bit bigger. There's some difference in the layout within the walls, right? So in the left one, there's some more constraint here. Like it cannot go into these parts of the layout, but here those parts are open. So then some more states in the right side, okay, than the left side. There's more valid states are much more. I mean, not much more, but a few more. Okay. So now let's see how the same 2000 episodes does here. Okay. So yeah, I'm just going to get started running this. So it's taking some time. It started off with 525 minus 525 minus 516 minus 517. I'm looking at the average rewards in the last 100 episodes. Okay, so here you see, there is some improvement, but it's a slow improvement, right? Minus 513, and you really cannot make out if there's an improvement or not. Okay, but slowly you will see that, maybe there is overall, that maybe there is some improvement. Yeah, sometimes you cannot even gauge it, right? Yeah, and now you see how it's performing. So it's behaving a little idiotically, right? Even after you did Q learning for 2000 episodes, it's dying. It's lost. It doesn't know how to proceed. Okay. So I mean, in terms of the state, the number of states, actually, it's not very different if you look at this, but still it doesn't scale very well. 2000 episodes are not sufficient. So maybe you need many more, maybe some 10,000 episodes. If you do, maybe it will be able to learn better. Okay, so I'll end this here, this particular set of plays. It plays 10 times, but I hope you get the idea, like what's going on here. And we will try to see what happens with approximate Q learning now. Okay, did it not close? Okay, and we ended. So yeah, so here it lost every time. So now on this layout, let's try to just do approximate Q learning. And the features used are, it's actually a very simple set of features that's already been coded in the Berkeley labs. So it uses some minimal features like what is the closest dot, where is the closest ghost, and things like that. But it's nothing very fancy. And what we're going to do is we're just going to train for 50 episodes and we'll watch 10 rounds of the game. Okay, so it's the same medium grid example. So let's do this. Okay. Oh, sorry, let me just make it a little bigger. Okay. So it finished the 50 rounds and it's already playing so well, right? It's just merely 50 rounds of approximate Q learning and it's winning every time. It's not dying. So you see that 2000 rounds, 2000 episodes of vanilla Q learning still was not helpful, but just 50 rounds of approximate Q learning really helped. Okay, and it's won every time. Okay, so that's kind of the power that these kind of generalizations or machine learning offers to you, where from some instances you can learn things about some other part of the space. Okay, thanks to these kind of functions. And you can even do something for larger layouts. So I'll just show you one last one, the medium classic layout. Yeah, so here also it's just 50 episodes. So this one would take some time because there are like more states to update. It's a slightly larger layout. Yeah. So you see that it's just going on its own. It's not chasing behind these scared ghosts because I guess the features don't make use of that part. But by and large, it's running. It's trying to like seamlessly going through, right? And it's winning. It's escaping from the ghosts. So it doesn't realize that this is actually like a larger food pellet. So it's running away from the ghost even when the ghost is scared. But that is something that you can improve, okay, with choosing the right features. And see, it's one again, right? So this is in some sense like you're seeing RL in its true action, like all this Q learning, and you made it. I mean, you can see its power. And see that, I mean, it's the ghost has chased. Okay, it's now it died. So sometimes this also does happens, but the good thing is now each time this is playing, it's also learning something from in the process. Okay, so it plays this episode, and it will update its Q values. Something went wrong in the layout, or okay, no, that was a ghost. Okay, so anyway, I hope this has given you some ideas about where you use Q learning and its utility. I hope you're able to see it, and more generally, even for real problems, you can use Q learning and approx Q learning. So if you're attending this workshop on deep reinforcement learning, actually I think there are some sessions on Saturday. So those are primarily by people in the industry. So there you will also see how they're solving like large scale problems, and that should give you a good perspective on this. So I would urge you all to at least try and see. Okay, so sometimes some of these talks can get like very technical, but I think you guys have a flavor now of Q learning, right? You've seen it in the course, so you would at least get a high level picture of what is going on if you attend these talks. Okay, so yeah, so any questions so far? Any thoughts on Pac-Man or these examples that you saw?
Ma'am, so
Yes, Anju?
approximate Q learning is basically a better version of vanilla Q learning. So,
Yeah,
in
yeah.
real life, do we even use vanilla Q learning?
Yeah, so vanilla Q learning you can use if your states are not very huge, right? If it's a small kind of system, then it's fine. You can use it, right? But typically what happens is, in real problems, it's not like that. Like you'll have a lot of states. So then, yeah, Q learning, vanilla Q learning versions may not do really well. Okay, so yeah, I mean it's entirely dependent again on the domain, but yeah, in most real applications, what gets used is the approximate version. That's more useful, right, than vanilla Q learning.
Okay, ma'am.
Yeah. Any other questions?
Ma'am, in approximate Q learning,
Yes.
we,
Yes.
as you say, we already know the states of ghost and food particles.
Mm-hmm.
Yes, but in like real life problems, we don't know these things, so we have to rely on vanilla learning.
No, actually, even in the approximate version, the thing is like, okay, currently you know where the ghosts are in
Yes.
each state, but if you take an action, you don't know where the ghost. I mean, the ghost is also going to do some action. You don't know where you're going to land up in. The next state is something that you won't know, right?
Okay.
Sahil, was that your
But
question or?
yes, yes. Like I'm just saying that we already know the states of ghost and food particles.
Mm-hmm.
So I think approximately Q learning just perform better because of disadvantage over vanilla Q learning.
No, so approximate Q learning is not okay. So this point is the same for vanilla Q learning also. current state, I mean, if you look at the current state of the board, of the layout, you know Pac-Man position, and you know where the ghost is at the current instance. Okay, that's the current state even in vanilla Q learning. Okay, but what you don't know in approx Q learning is, you know, what happens in the next state. That's something you don't know, and you don't know the transition probabilities. All those things you don't know. I mean, that's the same even in Q learning, but only difference is what kind of data you're seeing. I mean, the data you're seeing is also the same, but the kind of updates you're making, right? The knowledge, the information about the states, that is all the same in both vanilla Q learning as well as approximate Q learning. The change is only about how you make these updates. So you don't model the exact Q function in approx Q learning. So in vanilla Q learning, what you do is you're directly going to do this update here. Okay, so that's the only difference. Rest all, you know, what you know about the states, what you know about Pac-Man, that is the same for both. It's only in the update you have an additional model in approx Q learning because of these breeds, and that is what is helping you. I mean, there are these features, but these features are something that you can construct from your state and actions. Okay, it's not something like very new information that you know that is not there in vanilla Q learning. This is available, but it's just that you have to utilize it to generalize about the behavior of other states. Okay, so that's the difference in approx Q learning.
Okay, ma'am.
Right? Yeah, that's a good point that you asked. Yes,
Ma'am,
Rishabh?
is there any sidewise case for where the vanilla Q learning is better than approximate Q learning, or it will be always compulsory that the approximate Q learning is performing better?
So this thing, it depends, right? So sometimes if you don't have a very rich data, or you know, sometimes maybe there is no necessity to do this kind of a modeling. If you have a very small set of states and actions, then maybe this is not even necessary, right? So in that case, maybe this, you know, doing an approx Q learning can be an overkill, right? Like maybe it's not, you know, that much richness is not required in some sense. Okay, so in that case, you know, vanilla Q learning could help, right? So you have
Ma'am,
to see like whether it's really needed, whether the generalization is needed or not, right?
and
Like
so
for
according to you, if we have a small amount of data, means we don't have too much information regarding the states and other thing, then we will go proceed with the vanilla Q learning. And if we have the enough data, then we will proceed for the approximate Q learning.
So it's there are two things, right? So it's either it's about the amount of data that you have, and also the underlying MDP, right? Like how many states are there in the MDP, right? So what I'm saying is, if the number of states in the MDP is very small, then you don't need to go for approx Q learning. So the number of states and actions. So for some of these examples that you know you've been trying in the midterm and maybe the assignment, right, the theory assignment, it's a very small set of states. So there, if you try to do approx Q learning, it may be an overkill, right? It's not just about the data. So having more data always helps, even if it's Q learning or approx Q learning, it's going to help. But it's about your underlying MDP itself. You know, that MDP model, whether it requires something like approx Q learning or not. If it's a simple MDP, you can do just with vanilla Q learning. Right?
Ma'am, if we take the example of the chess game or something like that, so
Mhm.
in that case, we will go with the this vanilla Q learning, or we will focus on the approximate Q learning.
So in chess game, like what is the number of states?
Ma'am,
Uh,
too
it's
large.
it's too large, right? So if you just go with vanilla Q learning, what would you need? You need for every state, you need a sample point. For every state action pair, you need a sample point. Okay, you need a couple of sample points for every state action pair, right? So like I was mentioning yesterday, the ratio is about 10. For each thing that you need to estimate, you need 10 times the number of samples. Typically, that's a rough guideline. So are you going to be able to get that for chess, right?
No, ma'am.
You won't get that. So then, you know, approx Q learning is going to be better there, right? It's
And
going
so
to,
basically, in the means real life projects, where we don't generally we don't have this much data in real life projects, so we precisely focus on this approximate Q learning only, not means.
Yeah. So when you don't have too much data, you have to try Approx Q Learning, but you have to use simple functions. So in Approx Q Learning also, this is a kind of the most simplest form that you can take, a linear Q function, right? So something like this would work fine. So you saw even the Pac-Man example, just some 50 episodes, it helped even larger layouts, right? But if you have like a complicated function here, then you will need even more data. Right? So data helps you decide, what kind of models that you have, what kind of model you can use in your Q function. Okay.
Okay, ma'am. Thank you.
Yeah. Good. Okay. So I think kind of running out of time. So what we'll do next is, I just want to give you some hint about what the next topic would be. So this kind of wraps up our discussion on reinforcement learning. And we've started this thing about machine learning algorithms. So linear regression is a classic ML algorithm. It's a classic ML problem. So what we'll focus on starting from the next class is some models in machine learning. So what we are going to do is these models called probabilistic models. Okay. So just to give you some sense of this, I'm just going to take about 1 or 2 minutes. Okay. So here, what we did in this linear regression example, coming back to this, was that you had these sample points and you tried to estimate one value of W, right? And you did some updates, a gradient descent update, and we kept doing this to finally get this point. Okay, so maybe this was the W star. So this is the optimal value. So our hope was to come here, and we were interested in only this final value, a single estimate. I mean, there's a vector, of course, but it's a single estimate. Okay. Now, more generally, you can be interested not in a single estimate. You could try to do some kind of probabilistic notions. So what is the probability? You could model W itself as a random variable, and you could try to get what is the probability that W is some value W bar given your data. Okay, so these are some questions that people typically like to see. So there's one estimate you can get by solving this kind of an optimization problem, but can you get a set of estimates? And maybe this probability, there could be other estimates also which are not too bad, right? And sometimes people like to get a sense of all possible solutions for the problem. And then this kind of probabilistic queries are something that are very useful. And so you will see different kind of examples. Like you can depict this as a graph, and there'll be different kind of random variables playing in the system. For example, here all the y's that we get, these are samples of another random variable, okay, of the target random variable, and given some output. So these y's and x's are what you have. Okay, so this is actually the x's and the y's, this whole collection that you have. So that is the evidence that you have, and you're trying to find what is the likely estimates. So how do you do this more generally? I mean, in real systems, sometimes you might have a lot of such parameters. So I can just show you one. Okay, I don't know if I have it open here, but anyway, so you can have a very complex network of interactions. And in that case, how do you in general compute these kind of estimates? Okay, so that's going to be the focus. So this is a topic called Bayes network. So Bayes network. So this is what we will start from the next class. And so I would like you to brush up on your probability course that you did last time. Things like conditional probabilities, independence, Bayes rule, chain rule, and all these kind of things. So you can use this time that you have till the next Tuesday to revise on this, because this will make use of all these concepts heavily. Okay, so so I'll stop here for today, and thanks everyone for coming. Okay, see you on Tuesday.